Okay. So what big, huge-ass atom, Robert, is flying through this flame?
It looks like that thing that's going to hit me. The remote control.
What atom?
Sodium?
Sodium, yeah. All right. Or it could be, what did we do wrong on the AA?
Could be that you have the acetylene.
Yeah, that acetylene knob is too far, right? 'Cause that would give a... That's more yellowish. This looks more orangish, but it could just be the photo. But yeah, you can mess up the flame just by having the fuel. Okay, so here's some. We're finished wrapping up AA today on day 16, right? And here's a table that I just got from the book. What flame type are we using, Kathleen, in our AA? Do you recognize it? Acetylene, and acetylene's a fuel, and yeah, that big yellow tank, it says industrial grade air on it. Yeah, that's that one. Okay. No point in buying really purified air. It has a temperature range, it looks like. Fine, right? And it has this maximum burn velocity. All right. What is the point of all this, do you think? Anna, what's the point of... I mean, you have a flame's a flame.
I like the air on the rockets.
Oh, I did. Wow. What's the point of all this? You can have it on different, right? Different gases, right? It's hydrogen, oxygen. Hydrogen. Why have all these different types of fuels and flames? Oh yeah, interferences are going to be a problem, and just think all these different metals. Are they going to all behave exactly the same in the flame? No, right? So, and what do you want in that flame? If you want to study copper in Lake Elmendorf, what do you want in that flame, Rob?
Copper.
Be more specific though. Copper. Copper atoms. Think of all the options you've got here. This is a metal, right? You've got Cu plus 2. Yeah, this could be ionized. There's, right? That, if it's ionized, Cu plus 2, Cu plus, that's going to have a different line spectra, a different everything, chemistry in the flame than copper atoms would. It wouldn't absorb. So you could be loaded with Cu plus. You try to do this copper analysis. You say, oh, there's no copper there. No one's going to hire you again. Right? It's loaded with it. Right? You didn't do the AA spectroscopy right. Or it may not be Cu plus. It could be what? It's in the flame. Cu3 plus. Yeah, get off the ion thing. It could be what else? Copper. Not copper. Well, I guess you get it Cu stuck together. That's not going to be very common though. But if it did, imagine. All I'm trying to say is you get off of Cu atoms. It has a different spectra, different line spectra. You're not going to see it. Oxides. These metals form oxides really easy. All metals do. Right? Copper oxide, iron oxide, aluminum oxide. Everything, all these metals like to react with oxygen. And oxygen's in the atmosphere, so it's pretty easy to form. So by having different temperatures, we can, it's easier to run different types of metals. And if you look in the AA cookbook, they might say, oh, you should have a nitrous oxide, right? They specify the flame and all that kind of stuff for different types of metals. So how about this column, though? Why would they care? Right? I mean, Adriana, why would they care? Yeah. What is burning velocity, Adriana?
I meant to ask him, not you. I'm sorry.
Burning velocity. Well, I see the centimeters per second.
Yeah. So what's going so many centimeters per second?
The gas.
The gases. Right. Now, Randy, why would we be caring about the speed of the gas going into this burner head? Yeah, it's a flashback thing. Because if it's not going fast enough, The flame's going to go ink down into the burner head, into where all those baffles are. Right? So it wouldn't be a good thing. So that's really, to me, in my opinion, the only reason why that burning velocity is there is because of this flashback concern. Okay. So some things you have to be more worried about than others. Like, look at this, like acetylene oxygen. That's a really high flow rate. Right? Yeah, Pablo, we're going to be able to answer it better in a little bit because we're going to talk about different metals requiring different temperatures and different positions in the flames and all that. So that's really it. The whole purpose of different flames is the temperature so you can analyze different metals. Right? And we'll be more specific in a little bit. We talked about burn velocity. Now, since we're in this room, I can't demonstrate flashback, but because we don't have any gas, right? How could I demonstrate burn velocity, Pablo? You have to use your imagination here. We hook it up to Rob. He just had beans last night, right? All right. How can we demonstrate burn velocity with a Bunsen burner, hooking it up to a flame, hooking up to the little nozzle, right? You flick it on, you get it going. How could you demonstrate burn velocity? Yeah, how can we adjust the flow of the gas? Yeah, turn the little knob, right? Okay, and there's also a knob that adjusts the air intake, so you can crank the knob up really high. And if you crank it up too high, I mean, there's only a range where it's really pretty stable. That's another point of burn velocity. You want it to be a nice, stable flame. If you crank it up that knob too high, did you ever do that on the Bunsen burner?
I would never do that.
What happened to the flame? Yeah, it turns blue, but like if this is the little burner head.
Yeah, it's kind of like the whole thing.
All right. Yeah. I'm just going to open up that methane knob as far as it goes. Do you see what happened? The flame, before it was a nice blue flame, right? However, if you open it up, it starts making a lot of noise, and the flame actually starts up here. Right? And it's right? But the flame is above the burner. It's really unstable, right? You can make it go out easy. Go the opposite way. You can get turn it really, really low. You can get the flame to be inside here. Right? So it's not a good thing. Now, at least with a Bunsen burner, there's no little chamber down there. You have all these where this little gas can collect and have a little explosion going on. Bunsen burner is just a straight column, so you can't have flashback. And if you did, there's nothing to flash back on. Okay. But not so in a AA. You got the nebulizer assembly. Components of a flame. Okay, Ricky, where's your photographic memory here? You looked at this, you read it. What are the zones, the components of a flame? Do you remember this?
Inside.
I know there's a cone, yeah. I know that's being inside cone, but I'm not sure which one.
All
About
right.
the middle one I'm going to go with.
No one remembers writing these down? They should have been a bold and italicized word. No?
Pablo told me to go ahead, so I won't remember last time.
Here's your choices. Primary. Really, you shouldn't write 1 degree, because I don't think the book does that. Primary. Secondary. So primary combustion zone, secondary combustion zone, and the interzonal region. Maybe they weren't bold. I'll have to look. No one remembers reading this. That's all right. Okay, so where do these parts go? Ricky, you got a 33.33% chance of getting one of these right.
Okay, I'm going to go with interzonal region. There's a little small one on the bottom there. Oh, damn it.
Kathleen? Adriana?
The primary is the little one in the middle. The secondary is
Anna?
the primary is the outside.
Where we're at, John?
What should be choosing?
Where is the gas?
Primary has to be.
Primary is the top right.
Yeah. It's the top right line, so it's the middle chunk.
So think of, okay, like if you take a closer look, there's kind of a hint in the words here, right? Where is the gas coming out in this flame? On the bottom. So most of it's going to burn, right away. So you probably hit the what region right away? Primary, right? It's primary. Right? This is where it's first coming out, right? The gas.
Yeah, I said that.
No, you said the outer one, didn't you?
No, I said
Oh,
primary is the middle one and secondary.
Well, middle one is this.
Yeah.
This is middle,
No, I mean
right?
the little, I said
Okay.
the little one.
Ah,
Oh my gosh.
Okay, so primary, right, comes out of the nozzle first. The middle one, the interzonal region.
Little with an L.
And then you have the atmosphere out here. So then you have one more region where, last spot where it burns up, the secondary,
What is it?
right?
Primary, what's the line?
Combustion zone. So yeah, secondary combustion zone, primary combustion zone, and the interzonal region, right? Okay. So here's a plot of the distance above the orifice and the burner tip. So in our little schematic here, Kathleen, of our flame, where is this burner tip? Yeah, this chunk, right? There's our burner tip. Orifice must be where the gases are coming out, so right there. Okay, so here's our plot of temperature, distance above the orifice, and the burner tip. So where does it look, Alice? In what region of the flame is it really the hottest? Yeah, with a temperature of 1863, yeah, degrees Celsius. That's where it's the hottest, in the interzonal region. Where do you think, would you guess, Anna, is most AA spectroscopy performed? Where would you guess? It's not quite that hot there. In the interzonal region. In fact, this is easier to guess if I can show you, if I had a Bunsen burner going here. Because you'd have this really, bright, if with a Bunsen burner, you have this really bright blue region down here, and it's kind of bouncing around, right? And then you look right above it, you've got this really light blue, if not you can almost see through it, region. But you don't see any bouncing around going on in there at all. Much more stable region for combustion, right? And then you have the very outer rim where the flames kind of go, and you see some color there and things going on there. So the question really is, why is most, if not all, the spectroscopy being performed in this interzonal region? It's the hottest. It's the most stable. No, those things they help. They're really not the best answer. It has to do with the atomizer. Because what are we trying to analyze? We're studying the absorption of what? Atoms. That's where they're at. They're in the interzonal region. If they would be in the primary combustion zone, well, that's where we do our spectroscopy, because that's where they're at, even though it's not too stable, even though it's not too hot. It just happens that the interzonal region is where pretty much all of our atoms are, and that's what we're after. Okay. All right. I guess I should give some more hints here, just to head you up to see what's coming here. In this secondary combustion zone, you get a lot of oxides forming. Right? That might lead you up or give you some thought into what's coming up. Okay. Element emission profiles in a flame. So we have the absorbent signal is going this way, and then the height above the flame is going this way. So you'd have to have like some magnesium standard, chromium, or silver standard just sitting in there. And then you adjust the little knobs, which I didn't let you touch, right, to adjust the burner height. Okay, because we never did, right? We just shot the stuff and we were done with it. We adjusted the lamp. Okay, Adriana. Are all atoms measured at the same height in a flame? Man, you pick on her a lot today. All right, I guess, you know, no, I think a better way to say this, you know, would you perform the AA analysis at the same height for all metals in a flame? No, you shouldn't, right? Yeah, I mean, if you want to work with magnesium, you should be really high or really low in that flame. If you want to work with magnesium, would you want to be really high in the flame, you know, way above the burner, or really close to that burner tip? For magnesium?
I thought it was supposed to be like at 2.0 would be like the best. Is absorbance the most around there? 2.3.
Absorbance? You're analyzing for magnesium. Don't you want magnesium to absorb? Yeah. So shouldn't you be going where it absorbs the most? Right? So where does it absorb the most?
2.ish.
Right? Yeah. But that's not really close to the burner head. The burner head, really close to the burner head, is right way over here somewhere, right? So, but yeah, I guess it'd be better to say a number, right? That would have been better, right? So what distance? Let's put it that way. Everybody on the same page. What distance?
You gave us two choices. Too far away?
Around 2. Right? If you read 2 centimeters for magnesium, then you're reading this right. You're getting across what I'm trying to get across, right?
How does it measure a different?
Well, there's this knob that simply measures that changes the burner head, because that lamp is going through the flame, and we're not changing its position. All we're doing is bringing the burner head higher or lower. Okay, so that changes the height in the flame where you're measuring.
But if you don't change it, how do you get calculate?
So since we don't change it, is it that big a deal? Not really. If you were doing it would become a big to-do if you're doing a research project in Elmendorf and you come up to me and you say, hey, I can't see any chromium in Elmendorf. Okay, well, we tried everything that's easy. Now let's start digging into the hard stuff. We have to adjust the burner height. We have to adjust the nebulizer. We have to adjust, you know, every little parameter we can. Right? So it helps. I mean, what this is for is detection limits. Right? If you really want to push the instrument to its limits. Why would these curves be different? Like, look at, John, look at chromium. You want to be where to measure chromium? Where would you want to be? What height would you want to be to measure chromium? What's that?
2.5.
Well, there's a better height than 2.5. Pretty much right on top of the bloody burner head, right?
I was
But
looking at the CI, just looking straight.
look at silver. Silver is just the opposite, right? So what's going on there? As you get farther and farther away from the burner head,
Bigger atoms?
what's more accessible? Because remember, you want to analyze for these atoms. The problem is you're getting closer and closer to the atmosphere, right? The outside of the flame. So the higher you get in the flame, the more accessible oxygen is, oxygen gas is. And all this is just concentration. There's more oxygen. So which one, silver or chromium, really forms oxides in a flame? Super, super easy. Chromium. Look at chromium. Chromium, if you get him off of the burner head, right, he's forming oxides immediately. In fact, you get him somewhat high in the flame, you can't even see chromium anymore because it's all, the chromium didn't disappear. It's all what form now? It's all chromium oxide of some sort, Cr2O7, I don't know, but it's a chromium oxide. you can't see it because you don't have chromium atoms anymore. Silver, though, right? So why would the signal for silver be going up? It doesn't form oxides. It just must be that there's more what way out there around 4.5 centimeters. There's more silver atoms. Yeah, that's all.
What?
More silver atoms, right? So silver's behaving. Okay. Something funky's going on with magnesium. Remember, there's a temperature differential as you go up in the height. So probably what's going on with magnesium is it drops off probably because of what? It's reacting with oxides. So you should just say oxides, right? Oxide formation, magnesium oxides, right? But in here, really close to the flame, it's probably because it's Mg plus 2. It can't be oxide problem. It has to be something else. So it's probably, the only thing I can think of is an oxide, is the ion, Mg plus, or Mg plus 2. So there's an optimum position for magnesium. Kind of a weird looking curve there. Okay. There's a couple deficiencies when using a flame as the atomizer. Oh, Emily, can you think of something that's wrong with our atomizer? This is a hard question to answer. What sounds it's missing out on? When you run the AA, Emily, when you ran the AA, where did pretty much all your sample end up? Even this is kind of hidden to you.
Is it the waste?
Yeah, it's kind of hidden to you because everything runs down the little tube and it's kind of hidden under the cabinet. But pretty much everything goes to waste. Is that a deficiency? Yeah, right? You missed out on pretty much all of your sample, right? So pretty much all of it goes to waste. So that's one deficiency. It's kind of the same thing. I might as well just tell you this one. That, right? The other one is a tenth of a millisecond, or 10 to the negative 4 seconds. Someone figures that's the average amount of time your analyte really spends in the flame. So it's there for such a very short period of time. So the ones that you can see, right? The ones that don't go into the waste. Okay, great. Oh, wait, well, no, this didn't go into the waste. We went into the flame. Well, it's there for only 10 to the negative 4 seconds. So it's not very much time. Okay. Yeah, so why not fork out more bucks? Why not fork out about, I'd say, like $40K additional in comparison to what we have? You buy something called a graphite furnace, which uses electrothermal atomization. All right. Kathleen, what would you guess that is? And it's supposed to totally wipe out these two deficiencies. So what could it be doing? I don't know what the word graphite is in there. I think that's what it used to be constructed out of.
Use electricity.
But use electricity to what?
To burn.
To atomize stuff, to turn stuff into atoms. Is it going to go anywhere? No, exactly. They're going to have these little, I don't call it cuvette for lack of a better word. I don't know what word they use because we don't have one. But a cell, call it a gas cell or a cuvette or whatever, but it's going to be all sealed up. So for the AA light to pass through, and you pretty much just have to push a button, it atomizes whatever you put in that little tube, right? And it's going to keep it there, right? And it can't go anywhere. So you use everything, so there isn't any waste, right? I guess the waste would be whatever doesn't atomize. Probably not everything atomizes. There's probably still some waste, some residue on the bottom, right? But it uses everything you shoot in there, and then there isn't. It's in the cell. There is no residence time. It's there. So there's some real advantages. Problem is, well, that's a problem, but also you want to do a research project or any project, you have to be changing these tubes out, right? And they're about $20 a tube. So our lab fees are about $40, so that would kind of wipe them out pretty quick, right?
Wait, so you put one in for every sample that you do?
I bet you can get by with using the same tube a little more than once, but
So basically,
I think you pretty much got to be changing those tubes out.
We use AA.
Okay. So what's that?
Why do we use AA?
All right, answer your own question. Think about it.
It's cheaper.
Why do we use now? This is still AA. It's just called graphite furnace
What I'm
AA.
saying is it's either you have a crap load of waste and very little time for your sample, or you have to be the president.
Be the graphite furnace. So your question is,
It's cheaper.
It's like,
why use the flame as the atomizer, or why use the graphite furnace as the?
Why do any of this? Why do any of this? Why do any of the AA stuff?
Okay, why do any? Good question. Why do any of the AA stuff? We've got a GCMS upstairs, right?
I don't know what
Your grandma's name, Rob, is what?
Zeleznikov.
Okay. Bob Larue. She says, Rob, my water tastes horrible. It's because of all this iron. Or she watched that movie about chromium-6.
Do you know my grandma?
There's this chromium-6 in my water. I just watched the movie, and now the neighbor says it's in there. And she eats at McDonald's all the time and has lunch, and all these people are complaining that they're dying. Let me finish my story, right? So she's really worried about this chromium-6. So Rob says, hey, we just got a $60,000 GCMS here at Our Lady of the Lake. He goes up there and he says, can you analyze for chromium-6? Or can you analyze for it? You can't analyze for it. Does it vaporize? Do metals?
No.
Right? You're not gonna get it on the GC. Okay, we've got a $35,000 UV vis. Let's go shoot my granny's water sample on there to figure out the metals in there. Will that work? No. Oh, okay, we got a $45,000. Pick your instrument. FTIR. Will that work to figure out the metals in Granny's water? No. NMR. Ooh, we got a superconducting NMR. We just got a $250,000 superconducting NMR, top of the line. Can we analyze Granny's water with that? No.
Okay, so it's just for metals.
Yeah. Now, I am lying a little bit. You can do, if you figure out the right reaction, right? You Google it, figure out the right titration, the right reaction, and you can use a UV vis. But it's going to be messy and sloppy and a lot of chemicals just to figure out one metal. So that's why we have the AA. Okay.
Granny's water in the metal. I had
Yeah.
that conversation. I just saw on the news. Oh my God, no, wait, what version?
I don't know what that whole story was about, so it's weird.
Okay, Ellis, is a different lamp used for each metal when doing AA spectroscopy? Is that right? Does everybody agree? Yeah. Unless you buy a lamp that has, well, they don't have everything, but they can have more than one. We have some lamps upstairs that say, I don't remember, sodium, iron, and copper or something.
It says other metal.
Yeah. So
Miscellaneous.
So you can, but you can't. It's not that easy to do, and you can save a little bit of money combining more than one element on a lamp, but it doesn't work out so well. So you have to be careful. But pretty much, Alice is right. The answer is yes. So, and the idea there is, right, if you want to analyze for sodium, well, what better than to use sodium light? If you want to analyze for copper, what better than to use copper light, right? Because that lamp is made with copper. So why not solve all of this, right? And have, have your little fancy light source, right? And then have a what with slit widths? Ricky, what is it called? A monochromator, right? And, ooh, what color is sodium light? Orange, okay. Well, I'll get rid of the word sodium. That's right, orange light. Right? We could, you have a light source and monochromator. We could, hey.
Because orange light isn't sodium.
Yeah. Well, light is light, right? How does the dang sodium atom know that, ooh, this light was generated from a sodium atom or this light was generated from a monochromator? Wavelength is wavelength, right? Electromagnetic frequencies, right? It doesn't matter. What's the problem?
Then you want to analyze the amount of whatever, but just analyzing light.
What you're after a what measurement? Absorbance. Now absorbance is the negative log of what over what? P over PO. Okay. So that means there has to be a change in intensity for you to make an absorbance measurement. You with me so far? Okay. Your analyte, your metal atoms, what does their absorbance spectrum look like? What does their absorbance spectrum look like? They were, starts with an L, they were lines. Extremely narrow. Now there was some width to them, right? But it's extremely, extremely narrow, right? Okay, that's your metal atoms, absorbance spectrum. What does the light look like coming out of here? Right? If we would plot it, right? Wavelength and I don't know, intensity or something. All right. Well, no, we have a monochromator, so it's not going to be continuous. And we can center it, right? I don't call this lambda 1. So we can center it at lambda 1, but it's going to be really what? Wide. It's going to be much, much wider. I mean, if you actually plot it out, it still looks kind of narrow, because I mean, it's a monochromator and has all these nice fancy slit widths and things, so you can kind of narrow it down. But when you compare the two, man, there's no comparison. That metal atom is super, super narrow. So do you see the problem? If this is my intensity, sorry, if this is my incident light, right? I want to use this. I don't want to use this. I want to use this as my incident light. I have to measure P and P naught. Can you do it? Because the incident, no big deal. It's right there. But how would you measure this? Would it change this guy much at all? What is the... So this is my incident. Essentially, I could just subtract out the absorbance spectrum of my sample. If it's going to actually do the absorbing, just subtract it out. What's the absorbance spectrum of my analyte look like? Isn't he this guy? So take this big, fat, huge structure, subtract out a little dinky bit. What would it look like? Oh, I don't know. It might look something like maybe a little dip there, right? Because it absorbed, right? Absorbed that little bit out. So that would be my transmitted intensity versus wavelength, right? You can't, detectors can't tell that. There's not a big enough change in intensity. So instead, you use a lamp made with that metal. So here's my incident intensity. And then that incident intensity strikes the sample, right? Strikes your analyte. It does some absorbing. What would your transmitted intensity look like if sodium is there, right? Well, now you can actually, now it drops down to, I don't know, something lower, right? It can actually, it's easy to measure. Make sense? You can actually detect the changes in intensity. And you have to, otherwise you can't do an absorbance measurement. That's why no one uses, and physically can't make the machine. Can't make it work. Okay? You can probably get signals out, but it's not going to be linear at all. Okay? So the reason why you don't use a monochromator is the incident intensity is just too dang wide. It's too big. Its intensity is too large. In comparison to the absorbance signal of what you're measuring. You can't measure changes in intensity, which is what you have to do. Because this is the center of it. The center of it is right there, of the argument. You have to be able to measure and distinguish between P and P naught. If you can't distinguish, there's no absorbance measurement. Okay. How does a hollow cathode lamp work? All right. Maybe start with this. The cathode is covered with the, everybody, louder. Well, Robert sees it, right? The metal or the element of interest, right? That's what, okay. So, how does it work though? Filled with an inert gas, neon. What the heck would this inert gas be doing there? Yeah, you remembered it really well. Okay, remember over here? I was standing over here. I had this fluorescent tube. And then I was waving what near it? Yeah, huge electric charge, right? Well, huge voltage, right? And then the inert gas inside, which is probably argon, right? Somehow it started slamming really hard against the sides, and this material is white coated, and when atoms hit it really hard, this emits a broad range of colors, Roy G. Biv. Remember that? Why did these argon atoms inside this fluorescent tube started flying really fast in the first place when I brought a charge really close to it? Shoom! She goes flying off. Do you remember why? If it's an argon atom, or neon, whatever, it's a noble gas. Think of it as this sphere, right? Because the electrons are evenly distributed. There's no reason for it to be charged, or the P word, polar. There's no reason for it to be polar. But, you have these little collisions. Argon collides with argon, or collides with the sides. You get an instantaneous dipole. So that one dude who has an instantaneous dipole, he's the only one who feels a charge, who feels a really high voltage. And he goes shooting off. Or he goes shooting towards it, right? Depending on his induced dipole. That's why the neon's in there, right? So there's this huge voltage difference, but the neon is going to start flying around just because of those induced dipoles of it. It's going to hit stuff. It doesn't really do any good if it hits the glass. But if it hits the cathode, right, where that metal is, right, it's going to kick off a little bit of that metal. And that's how it's built. It's built so that it's going to release a little bit of that metal. Copper, pretend it's copper. It's going to kick off a copper atom. And a copper atom has a lot of energy. So it emits copper light. The problem is that it's still floating around in here, right? You have this, literally, you have this copper gas floating around in there. So the more this happens, the more these neon slams into the cathode, releases these really high energy copper atoms, and they emit copper light. There's no oxygen in there, so it can't emit copper oxide light. Right? It's just copper atoms. And then you have, so the idea for this lamp to last as long as possible is for this copper atoms to settle back onto the what? Cathode. You want to redeposit them. So how do they do it? Well, the best they can come up with is a tube shape. That seems to work. And then they also that's all they, right? That's all, because you can have different shapes for it. The tube shape is just, the cylinder shape seems to help the most, so that's why they're all shaped this way. And then there's also, you see this, I'm going to pass this around, you see this kind of shiny metal thing going around there. So that helps generate some fields to try to redeposit the metal back onto the cathode. And that's about it. Right, so why are they cylindrical? What stuff?
Metal.
The metal. Yeah. To help that lamp last as long as possible. Because if your lamp only lasts a week, people aren't going to buy the darn thing. Okay.
Is this like mercury on the inside of the glass? Or?
No, it's just metal they deposited on there. spectral interferences, absorption spectrum interference overlaps with the metal of interest. Okay, so you analyze Elmendorf, and there's a bunch of crap in there, right? That's absorbing the same wavelength you're interested in. So you have to push the little background correction button. And if we would have done an Elmendorf sample, we would have had to have done that. Okay, we had to add lanthanum. We had to add lanthanum to some samples when we did a certain metal analysis. And the reason was that darn metal, it easily ionizes. So lanthanum just suppresses ionization. Lanthanum releases a whole lot of electrons into that flame. So if there's a whole lot of electrons in the flame, would it be easy for something to ionize? Well, right when it forms an ion, there's a whole bunch of electrons there. It's just going to go back to forming the atom again right away. That's why it releases all these electrons in the flame. So it suppresses ionization. So the last thing, and that's called the releasing agent. We use lanthanum. The last thing is this AA cookbook. Calibration curves are typically not linear. That's why you have to use the cookbook. All right, and you follow all the little specs in the cookbook. All right, you pick a concentration range you're interested in, then it tells you the slit width and the wavelength you should use. Someone did all this work, right? So that's about it. We went a minute over.